So it should be recording. So this is Muhammad Ayan, a chemical engineering student at Department of Chemical Engineering, VNIT Nagpur. And today I will introduce transport phenomena and especially molecular flux. So let's begin. In transport phenomena, we studied momentum transfer, heat transfer, and mass transfer, and correlated. Hidden connection between these three subjects, first we understand two examples. On the surface, the flow of river. On the surface, the flow of river, the heating of a skillet, and the scent of perfume across room appear to be distinct physical event. Deep down, the mathematics describing them is almost identical. These three phenomena is almost identical. Defining transport phenomena. Transport phenomena is the unified study of the movement of three fundamental quantities, such as momentum, like fluid flow, energy, heat, and mass. We study momentum flow, energy flow, and mass flow in transport phenomena. So, the evolution of engineering. Before 1960, we study separately fluid mechanics, heat transfer, mass transfer. Then, after 1960 onward, before the mid 20th century, these three subjects taught separately. Engineer eventually realized that solving the math for one system means essentially solving it for the others. So, in 1960, three professors from the University of Wisconsin, Bird, Stewart, and Lightfoot, formalized this unity. Their work proved that momentum, heat, and mass follow identical pattern, revolutionizing how we understand the physical world. So, the language of momentum flux. First we assume we see example here. Think flow of flux as traffic density. It measures the rate of flow per unit area. If high flux, 100 car passing the line per minute. If 100 car passing this line per minute, suppose that's high flux, and low flux, 5 car passing line per minute, say 5 car passing line per minute. So flux is nothing but flux is equal to quantity by area into time. Whether it is heat, water, or molecular flux, tell us how fast something moves across the specific surface. Two ways to move. There are two ways to move. First is convective flux, second is molecular flux. So what is convective flux? Convective flux is nothing but bulk motion. The water, suppose the water moves, so the leaf moves in the river. Yeah. Then molecular flux. Molecular flux means random motion. Molecular vibrate and collide, pushing the tea outward without stirring. Diffusion. The fundamental laws of transport focus on molecular flux. Movement driven by macroscopic chaos, not pumps or fans. Okay. Momentum transport. The mystery of the resistance. Why do some fluids flow while other resist. Think about it, like why do some fluids flow easily while other resist? Like water flows easily, but honey will flow slowly, have some resistance in flow. So Sir Isaac Newton defined this resistance as viscosity. Understanding the Sir Isaac Newton defined this resistance of fluid as viscosity. Understanding this resistance is the key to predicting flow. So Newton's law of viscosity in 1687, Newton's proposed a law, Newton's law of viscosity. There are two fundamental logic, fluids move in layer. First logic is fluids move in layer, and the second is the top layer drags the one below it, creating friction. So consider the below's layer is fixed plate, and upward above that moving plate. Yeah, so only top layer will move, and below that will be fixed. So the Newton's law of viscosity state as tau is equal to minus mu and velocity gradient. So tau will be shear stress, the force stopping the flow. Mu is viscosity, the thickness of the fluid, how thick was fluid is. Then this is the velocity gradient. Okay. Then energy transport, predicting in the flow of heat. Scientists always knew things got hot, but predicting how fast heat travels through a solid wall or metal rod was a mystery until the 19th century. The key concept thermal conductivity will introduce. Fourier's in 1822 proposed a law, Fourier's law of heat conduction. There are two main logic. Heat always flow from hot to cold. The steeper the temperature drop, the faster the heat flow. The steeper the temperature drop, the faster the heat flow. Okay, the temperature drop, the faster the heat flow, and heat always flow hot to cold. Okay. So this Fourier's law is stated as Q is equal to minus K and into a temperature gradient. So here Q is heat flux, the flow of heat, crimson. Then K is thermal conductivity. How easily thermal conductivity is nothing but like how easily material transmit energy. Then dt by dy is temperature gradient, the difference in temperature over distance. So the mathematical, so here are mathematical similarities between two laws we see. So we see this is the Newton used viscosity and Fourier used thermal conductivity. The specific variable change, but the mathematical structure is exactly the same. Like here only like viscosity or thermal conductivity will change, but the mathematical structure of both laws are same. Here in Newton's law of viscosity, the viscosity is driving force, and here Fourier's law of heat conduction, the thermal conductivity will be driving force. Driving property of medium. Property of medium. And driving force will be in Newton's law of viscosity. In Newton's law of viscosity, the velocity gradient will be driving force. Then in Fourier's law of heat conduction, thermal conductivity plays as driving force. From molecule to machine, we see these laws. We can say like momentum, heat, mass, flux are eventually are same mathematical structure. So understanding the molecular flux allows us to design massive pipeline, efficient engines, and life-saving medical devices. We can engineer the macro world because we understand the micro world. Nature seeks balance. Whether it's momentum, heat, or mass, the physical world is driven by the same fundamental rule. It is all just flux driving nature toward balance. So thank you. This is for today.